We'd like to welcome you to today's, and thank you for joining us for this installment of the Groundwater Foundation's webinar series, co-sponsored by the Water Research Foundation. All the attendees, we're still having some issues with attendees still trying to get into the webinar, but we're going to begin as we fill our way in here. In order to achieve the Groundwater Foundation's missions of educating and motivating people to care for and about groundwater, the Groundwater Foundation is offering these monthly webinars. While we continue to offer some conferences, seminars, and workshops, we feel the webinar series offers us the opportunity to provide valuable resource to you at a minimal cost and no travel expenses. My name is Brian Reitz. I am Program Coordinator at the Groundwater Foundation, and I'll be hosting today's webinar. And we're excited to have our presenter, Karen Griffin O'Connor with Olsson Associates. I just wanted to walk you through a couple of our webinar features that we have been using that we'll use during the course of today's event. First off is the chat feature. If you'd like to ask questions during the course of the presentation of me or the presenter, please type your question into the chat box just to the left of the send button in the bottom right-hand section. I'll monitor those questions throughout the presentation, and then we'll address as many of them as we can toward the end during the Q&A at the end of the webinar. So just to make sure, you should see down in that bottom right-hand section, there should be a chat function called up in the bottom. And then underneath it, there should be a button that says Send To. And then there's a button on the right that says Send. There's a little box there that you should be able to type your questions into. I will send a note to all the participants, so hopefully then that will come up on your screen. Secondly, we'll be utilizing the polling feature during the presentation. When a poll question is asked, the screen should pop up. So I'm going to put up a poll now talking about where you heard about today's webinar. If you could spend some time in answering that question, I think that it'll give you about a minute to answer that question. So.
Please send a chat to Brian. All right, so the poll results have gone through. I'm now going to introduce Karen,
who will be talking. Today's topic is sustainable groundwater development using GIS and groundwater modeling. Karen is a senior scientist with Olsson Associates in Lincoln, Nebraska. She has more than 15 years' experience managing multidisciplinary projects focused in the fields of geology and hydrogeology. She received her bachelor's degree in geology from Smith College and her master's degree from the University of California, Santa Barbara. She currently works on the Hydrogeology Team for Olsson Associates. Her current passion is redevelopment of brownfield sites, implementing new technologies to protect and restore our surface water and groundwater resources. So now I would like to welcome Karen.
Thanks, Brian. I'm really pleased to be here. Thank you all from the Groundwater Foundation for inviting me to speak today. Before I get started, though, I'd like to say if any of you are having a hard time hearing me, please send a chat note to Brian, and we'll change some things around here. And to start off, I'd like to begin with just a brief, fundamental introduction to groundwater geology. There's two principles of groundwater geology that I want you all to recognize. These are from my professor of groundwater geology. He likes to start out his lecture saying there are two laws of groundwater flow. The first one, which we won't really talk about, but I will just throw out there for you to ponder, is that water flows uphill to money. The second one, though, is what we'll talk about today, and that one is that there is no such thing as a free lunch when you're talking about groundwater. Now, you've all heard about the hydrologic cycle, water budgets, conservation of mass. I really think it's all just tied up in that statement, that there's no such thing as a free lunch. If you take some water out of the system, it's going to affect someone somewhere. The question is how long and how much. So that's really the main topic that we're talking about today here is sustainability of groundwater development. For the talk, what I'm going to do is, let's see, go to the next slide. Let's see. I think it does take a second for these to register, so I'm going to pace myself and keep it slow at the beginning here. The presentation for this outline, what I want to do first is I understand there's lots of folks from across the country and even outside of the country listening in today, so I'll give you a really brief introduction to who Olsson Associates is. And then I want to introduce the issue of sustainable groundwater development here in Nebraska. What are the questions that we're being asked by our clients to help answer? And to give you examples, 2 case studies of the GIS and groundwater modeling solutions that we've come up with for our clients. And then we'll open it up at the end with question and answers. Olsson Associates I like to describe as being the perfect size engineering firm. We actually have offices across the Midwest. We have a very diverse type of engineering that we do. We go all the way. We started out doing civil engineering here in Nebraska. We are based in Lincoln, Nebraska. We've diversified into all different kinds of fields, mechanical, electrical, transportation, land development. Personally, I work for the Hydrogeology Team here in Lincoln, and I'm just going to focus in on what we do primarily here in Lincoln. We do all kinds of investigations. We do assessments for sites. We do groundwater evaluations. We also do permitting for the energy industry. We are really well known for our air quality permitting. Air quality is an important aspect of a lot of different projects you don't even know about. And then one of the other fields that we're also very well known for is our wetlands delineations work. Let's start off, though, again, giving you a little bit background on the geology and groundwater of Nebraska, since that's where we'll be focusing on today. Most of you have heard of the High Plains Aquifer. The USGS has been doing enormous amount of work for years and years defining the aquifer and looking at what kinds of declines or increases have occurred across the area. I'm going to use this pointer. I hope you can all see that. This is an illustration by the USGS of the distribution of the High Plains Aquifer, and the colors here to indicate that it's not all flat out here. It actually does have a topographic relief going from high to low, and that's what the orange or reddish colors are high, and low being the green. Basically, that's the groundwater flow across the area as well. I do get this a lot. When I say I'm from Nebraska, people say, oh, I've driven across Nebraska on I-80. That's why I like to use this map. Yes, you have driven across the thickest portion of the High Plains Aquifer. In Nebraska, we are fortunate to have a thickness over 1,000 feet of the saturated thickness of this High Plains Aquifer. As you move south into Kansas and Texas, you'll see that the aquifer does thin significantly, and that's where the issues are even more dramatic. In this map on the right, we can see this is another map by the United States Geological Survey illustrating where there are declines. The red areas down here in Texas illustrate where there are significant declines in the aquifer. Up in Nebraska, where we have this thicker portion of the aquifer, we do have some declines in the western part of the state, but on top of that, on the eastern part, we even have some increases related to irrigation districts and reservoirs recharging the aquifers. What I want to also point out in this map, on the eastern side of Nebraska, we do get out of the High Plains Aquifer. And most of the work that the first study that we're describing today is on the eastern part of the state, outside of the High Plains Aquifer. Okay, and just a little introduction, too, about how groundwater is managed here in the state of Nebraska. The state of Nebraska has been divided into 23 natural resources districts, and these natural resources districts do more than just groundwater management, but I'm focusing, obviously, on this aspect of their work. And the reason that the state has divided the system up into 23 natural resources districts is that so that there is local control over the uses and of groundwater in the area. The permits to develop wells do go through the natural resources districts, and they therefore do have control on how much or how little development is going on in their area. And even though the state is primarily flat, there is a very significant difference as you go from the east to the west on the amount and the different uses of water. So that's why we've developed these 23 natural resources districts to manage the different aspects across the state. Oops. On top of the natural resources districts, over and above them is the Nebraska Department of Natural Resources. And the department has jurisdiction over the surface water as well as the groundwater. And they take into account the compacts that we have with other states, such as Wyoming and Kansas. And through their evaluations each year, they identify which areas of our state have become fully or over-appropriated basins. Those are the terminologies that we use here in Nebraska. The orange area meaning fully appropriated and hydrogeologically connected, meaning that you cannot propose new wells or new irrigated acres in these areas. Over-appropriated areas are where we've already gone beyond what's sustainable in a certain area, so there will have to be some cutbacks in the number of wells that are used in irrigated acres. As you can see, it's the western part of the state that's got the biggest issues. But just last fall, it was almost designated, the eastern part of the state was nearly designated as fully appropriated as well. So the natural resources districts on the eastern part of the state here are also looking at what kinds of management practices they can do to try to stay ahead of the game, so they don't become another NRD where the whole area is basically shut down to additional well development. So going on just to describe the two case studies that we'll go into today. The first one has to do with how to answer this question of how can we better manage our groundwater resources. And this was done using the GIS software that we'll discuss in a minute. It's basically an aquifer mapping project. It goes beyond that, but that might be a quick way to describe it. It was done for the Lower Platte North Natural Resources District on the eastern part of the state. And the second question that we were asked by one of our clients is, we've got a very large water user, and how will this new water user impact existing wells in the area? And for this question, we used a different kind of approach. We used a groundwater modeling approach, and this study was done for the Public Power Generation Authority in Hastings, Nebraska. So those are the two studies that we'll go into in more detail, and like I said, at the end, we'll wrap it up with questions on either one. So let's get started with the Lower Platte North NRD. The Lower Platte North NRD here on the eastern part of the state is approximately 1 million acres. The population across this area is about 61,000, and there's approximately 20 communities. This is primarily agricultural. As you can imagine, there's always an increase in need and increase in well development in these areas, and those are the kinds of things that this area was looking at. Omaha is on the east, just on the eastern side of the Lower Platte North here, on the eastern side, and then the other large population area of Lincoln, Nebraska, is just to the south of Saunders County. Basically, the NRD in 1999 had a certain number of wells across their natural resources district. The yellow dots on this map are all the registered wells in 1999. And you can see that in 7 years, the red dots on the map illustrated how many new wells had popped in. And seeing the writing on the wall with the western part of the state being identified as fully appropriated, the Lower Platte North asked us, are there ways that we can identify which areas can sustain additional well development and which areas cannot? So with that in mind, we started off looking at how do they currently manage their groundwater in this region. They had set up in their groundwater management plan 4 specific groundwater regions. The Shell Creek region is in the northwest part of their area. They also had the Platte River Valley region, which is right, the Platte River cuts right through there, so that's how they define that area. Then they had another region called the Todd Valley, which is this orangish color, and that actually is an ancestral flow path of the Platte River. And then that area cuts the Uplands area into 2 parts. So the red areas are the Uplands areas. And so basically they asked us, is there a way that we could subdivide these 4 regions into a finer detail so that we can manage our resources even on a finer scale than our 4 regions that we have right now? So as geologists in the hydrogeology group here, we always start out looking at the bedrock maps of the area. So we developed a sequence of maps of the area, and basically the GIS maps that we use will go into more detail in a minute. But the first map that we looked at was the Bedrock Geology map. And as I've shown you before, the High Plains Aquifer pretty much peters out as you go to the east. And this little teeny piece of the High Plains Aquifer is present in the northwest corner of the Lower Platte North. But the rest of the whole area is primarily fed by aquifers that are shallow alluvial aquifers. And so we weren't so interested in the bedrock geology of the area. We needed to look in more detail at the alluvial materials on top of the bedrock. So that's when we started with geologic cross-sections across the area. We are very fortunate here in the state of Nebraska to have the University of Nebraska Conservation Survey Division. And they went out for the last 80 years, I believe, and drilled test holes across the state. And these test holes were just to give us information on the subsurface geology. And for those of you that have mountains in your area, you don't understand how hard it is to do geology in Nebraska without these test holes. You basically are working in the dark. So these test holes are really our source of information for any kind of study that we do here. And the lines of cross-section that I've illustrated on this map that are in yellow, each dot on this line illustrates the location of one of those test holes by this Conservation Survey Division. Those test holes give us information on the subsurface geology, and that's how we build our cross-sections. So with that, we drew all these different cross-sections. I'm going to show you the one that goes down the central portion of the Todd Valley, which I told you before was where the Platte River used to flow. So if you think about a river system flowing in an area, it's going to deposit a lot of sands and gravel. And this, although it's spread out because it's a very long area in a large distance, it goes from the north to the south of the Todd Valley, and each one of these lines is where the test holes went down, and they describe the geology they encountered during drilling. And as you can see in this cross-section, the stippled dots across the cross-section illustrate that there is a fairly thick sand and gravel unit that's continuous from north to south, deposited by the ancestral Platte River. In this area, the Todd Valley, is what you can see a very long, continuous aquifer. And as you can see on top, there's a little bit of clay on the top. It's rather thin, so difficult to see at this scale. There's a brown color on the map to illustrate a clay unit. It's fairly thin, though, in comparison to the next area that we look at, which is the Uplands cross-section, again going from north to south, starting up in the current Platte River Valley and going to the south. You can see that instead of having that long, discontinuous sands and gravels, we actually have discontinuous sands and gravels. I'm sorry, I said that wrong. Instead of continuous sands and gravels, we have very discontinuous ones. Here's another sand and gravel unit, but as you can see, it pinches out to the north, and there's clay units in between. So you can see that a great difference in these two aquifer types, in that we have these discontinuous sand and gravel units in the Uplands area, whereas in the Todd Valley we have those long, continuous ones. Those are important for understanding what the sustainability of these aquifers are. If they're discontinuous, obviously they have a smaller amount of water that could be pumped from them. As well, these areas in the Uplands have a thick unit of clays on top, which means slower recharge. So in trying to figure out how to map out all these areas across the district, we recognize that the cross-sections only get us so far. There are only points on the ground in certain areas. The big areas that we were missing. So we looked at some other reports done by the USGS just to the south of the Lower Platte North and the Lower Platte South Natural Resources District. This was a study done in 1994, published in 2001, and you might say, well, why did it take so long? Well, the work was done before electronic data like we have today. And so what they did was they took, and we'll show you this in a minute, they took all the same area, the same kind of study, took to the south of our area, identified 5 specific aquifers. What we decided to do that's different was we decided to approach the problem, same general concepts, but use the Geographic information system that would allow us to look at the data on a much quicker time scale, rather than a geologic time scale, as we like to say. We pulled in information. This is just a general graphic to illustrate what a GIS system is if you haven't seen that before. With a GIS system, you can pull in information, meaning maps and data sets on transportation, for example, different types of vegetation for an area. You can also look at the hydrology of an area or just the boundary. With that, then you layer this information on top of each other, start to look at the maps differently, you see patterns. You begin to understand the system more than just one aspect of the system. So what we did in looking at the Lower Platte North area is we recognized that there is a huge amount of data out there, not just with those test holes, but with all the registered wells across the district, over 5,000 registered wells in this area. And we figured this is a great resource for additional information, although not to the level of effort that was done by the CFD at the University of Nebraska. They still provide the critical information that we needed to define these aquifers. And you can see there are certain areas in red on this map where the well density is very high, almost 8 wells per mile. Certain areas where the well density is very low, less than 1 well per mile. So there's parts of the map that we have more information in than others. But what we did was we took that information, which is now available electronically through the Nebraska Department of Natural Resources, and we took the information and brought it into a database. But let me step back just a minute and illustrate what it was like before. Before, you would take those well logs, which is what I've got illustrated right here, each line indicating what the type of material is that they encountered during drilling. And then there would be another map or diagram that you might look at that shows how the well was constructed. That was a time-consuming process, but now what we've been able to do is take all that information electronically into our Access database, basically, and be able to sift through. We have all the wells in this database, and we can just sift through them very quickly. This is just one screenshot to show you that it illustrates all the different units and as they are described by the geologist or the driller. And then also gives you information on water levels and well construction, all in one screen. So So we were able to look through all the well logs of the NRD, sift out the ones that didn't go to Bedrock, use the ones that were going to give us the information we needed, basically, and just focus in on those. And with that, we were able to come up with a new kind of map illustrating where these aquifers or these sand and gravel units are continuous. At each of the well points we identified, and these are the wells as black dots on this map, at each of the well points we did identify how thick the basal gravels and sands are. Anywhere there was a gravel unit that was continuous for over 30 foot in thickness, we looked at that as a continuous aquifer. And you can sort of begin to see the patterns here. This is the Uplands region that's cut across by the Todd Valley. In the areas where the sand and gravel units were thick, it's green. Where they're thin and discontinuous, again, reds and yellows. And so it may seem like this was a fairly time-consuming process, but once it got going, we really were able to go through these fairly quickly and get an idea over the entire district using all the well data that's out there, what kinds of thicknesses these sands and gravels have. So with that, we were able to take that thickness map, gravel thickness, across the entire district and map those sand and gravel units. The color schemes kind of change just based on the scale that we're looking at, but again, where there's green dots and circles, these are where the gravels are very thick. The red areas are where there are almost no sand and gravel were detected in those the well logs. And you can see from the way we've driven this, we had the four general regions, the Shell Creek region here. You can see begin to see a pattern of thicker sands and gravels coming across this northern section, as well another sequence of sands and gravels as you come down through here. And if you think about glaciation here in Nebraska, these rivers were flowing during the glacial period, and they were changing as the ice sheets moved and melted and advanced. So that's why the river system changed path. And by doing this mapping, we were able to see basically the ancestral flow patterns of these river systems. As geologists, we call these paleo valleys. So here's a paleo valley coming down the Todd Valley area. And then here's another paleo valley coming along the southern part of the NRD and into the Todd Valley. And that was the critical area that really the NRD was having issues with how much more development can we sustain. With Omaha to the east, Lincoln to the south, there was additional well development going on, and they wanted to know how much more. So in looking at that area, we kind of focused in on that in more detail, but these were the specific smaller sub-areas that we came up with. And as you could see before, I showed you there was a sand and gravel unit up here along the middle part of the Shell Creek. And then there was a pattern that we could see coming down through this Todd Valley. We did not subdivide the Todd Valley. That was a continuous aquifer. And then we saw another paleo valley coming down through the southern part here. And using those maps, what we were able to do was, like I said, subdivide the Uplands region into several smaller regions. And then basically what we did was we gave the information to the NRD, and they then decided where to restrict additional well development or not based on these aquifer maps. And so they came up with a map that they overlaid on top of ours, saying, based on what we know about the aquifers, we know that this area here in red in the center should have some restrictions to well development. And so they took that information and they posted on their website and in their groundwater management plan saying, we've got some good geologic information to illustrate the areas where we feel there should be some restrictions to well development, and other areas where the aquifers are fairly continuous and we can see that additional well development is sustainable at this point in time. So with that, that was really what we were trying to accomplish in terms of the hydrogeologic evaluation. We specifically delineated the groundwater regions into these sub-areas. We also developed a detailed geologic land use geochemical and a bunch of hydrogeologic maps. We didn't go into those in a lot of detail, but there were a series of, I think we did 25 different data sets that we developed into maps. and put those together as part of the report for this project. All those maps come together to putting together the different sub-areas. And all of that data was compiled into a GIS database that the district has for use now and into the future. And they do plan to post most of those maps up on their website in the near future. They do have some up there now. But the idea is that we've done this study, this information is available. Now you can all take a look at it and use it as needed. The news for the day, though, the good news for the day, is that the Natural Resources Conservation Service has actually provided some incentives and some great funding for the NRD based on this study. Just recently, the Lower Platte North was given $1.8 million in federal funds for these areas that have identified that they need to restrict water use. So they're now able to give those irrigators and those farmers some funds so that they can convert their systems from flood irrigation to pivot or go from irrigated to dryland farming, things like that. So although, it may sound like, wow, you're changing a whole lot of folks' lives or something like that. It could be an issue for these guys out there. Well, the truth of the matter is that if you don't look at the sustainability of these aquifers, in the long run, things are going to cause problems in the future. And this funding will help them with some conversions to other conservation practices. So now let's move on to the second case study. The other project that we were working on, it has to do with a site in Hastings, Nebraska, which is just on the east of where the fully and over-appropriated areas are in the state of Nebraska. So they can allow additional well development, obviously, in terms of even large water users. But the questions that they had asked are how will new wells affect existing wells in the area? So basically what we did, this is for the Public Power Generation Authority of Nebraska. There was a new power plant, that was being expanded. And during the expansion, obviously they're going to need some more water to cool those during the power generation facility. They'll need their cooling water to keep the towers cooled during operations. And so they needed 2 new wells. And these are fairly large capacity wells, 1,500 gallons per minute each well. And basically the community around Hastings, Nebraska, which I should illustrate, this is a aerial photograph of Hastings, Nebraska. The power plant is just to the east of town, and the 2 wells are illustrated on this map. Basically, the 2 new wells will have an average annual discharge of 1,700 gallons per minute with a peak flow of almost 3,000 gallons a minute. So the irrigators and the farmers and the industry around the area wanted to make sure that these new wells wouldn't impact theirs detrimentally. The good news, though, and why I wanted to bring this study up as an example, we've done several of these groundwater models for this area, ethanol plants and other industry coming in. Primarily, the goal for this study was this was a backup plan for the public power Hastings utilities. Their plans are to use the site to the south is the former Naval Ammunition Depot. And the former Naval Ammunition Depot has some contaminated groundwater issues. This is a Superfund site. Hastings, Nebraska is well known for, unfortunately, for the groundwater contamination in the area. And so the Army Corps of Engineers is planning to do a groundwater pump and treat system. And they will be discharging 4,000 gallons per minute constantly during their treatment process, which will go on for decades. And the plan here is to use that water for the cooling towers at the power plant as it expands. But what we're doing here was analyzing what would happen if that treatment plant was turned off and they needed to run the power plant. This is the backup water supply. So, again, that's a great example of how industry and communities can work together to reuse water resources. So, the study that we did for the Hastings utilities was specifically to look at how these new wells may impact existing wells. And the methods of our study included first defining the local hydrogeology and the hydrostratigraphic layers. And then we wanted to look specifically, once we know the geology, determine what's the source for the local wells, which layer are they tapping into primarily. And then we constructed a 20-year transient groundwater simulation. And the reason that we do this 20 years in the past is we've got good precipitation data, we've got well pumping data, and we're trying to predict the future, obviously. But we use the information from the past. We develop a model, we simulate the groundwater conditions, calibrate it to make sure that we're in the right range of flow patterns, and then we turn on the new wells and see how they would impact the system. And that's really what this 20-year transient simulation is all about. If you haven't heard of transient groundwater models, that means that instead of a steady state system where you turn on all the wells at one pumping rate and just see how it all equilibrates, we know here in Nebraska the irrigation system's 3 to 4 months, and so we want to simulate a change in the flow patterns throughout the year. So for that 20-year period, we would have the wells turn on during the irrigation system and then turn off. That's what it means by saying a 20-year transient simulation. And then what we do with that information, once we have the model up and running, is we calculate the estimated change in water level for the surrounding wells. And then we also calculate the change in yield for those impacted wells. So let's start with the local hydrogeology. As I mentioned before, this area has some history of contamination, so there's also a whole lot of history of evaluations done. So we have fairly good geologic information. The first layer is an unsaturated layer of silt called lust, and the second layer is an unconfined, or typically we call this the upper aquifer, and it's a sand and gravel aquifer, alluvial aquifer with some interbedded clay and silt. The third layer that we identify in this area is a confining layer that's made of clay, and it is discontinuous across the area. So what that means is that the lower layer, or the lower aquifer, is confined in certain areas, but it's not confined in others. So in our model, we have it identified as a semi-confined unit. This lower aquifer is about 100 feet thick, and it is sands and gravel. It's very coarse gravel, and it's a very productive aquifer. Just graphically, if you would rather see this in illustration, this is the groundwater model layers as we defined them. Layers 1 being the lust that's dry. Then you go to layer 2, which was the unconfined aquifer, water table about midway through that layer. Then the confining layer, and then the semi-confined lower aquifer. To simulate the area, we developed a groundwater model with a domain of about 11 miles by 11 miles. So this is an aerial photograph again of the area. Hastings is off here to the west. The power plant and the new wells illustrated in the center. And throughout these diagrams, I drew the 3-mile radius around the wells. Basically, what we wanted to know was how would the 2 new wells impact wells within the 3-mile radius. When you're looking at developing a groundwater model, you want to make sure that your edge of your model is far enough away from the area that you're trying to look at, because there's always edge effects to the modeling system. So specifically, we wanted to make sure that we could identify the impacts of all wells within 3 miles, and that's why we went out beyond that. Within this 11-mile area, we have over 500 pumping wells used for irrigation, industrial. There's an ethanol plant just to the north, and there's also the municipal wells for the city. One of the things we needed to find out, as I said before, was which layer are these wells tapping into. Now, we don't always have well construction information on every well out there. So what we did was we took all that we knew, that we had records on, and found out that all but 2 or 3 of the wells are tapping into the lower aquifer. So the other wells were actually just monitoring wells, and they weren't even pumping wells. So substantially all the wells in this area are pumping from this lower aquifer. In developing the groundwater model, we had to take into account, of course, the groundwater flow patterns across the area. So we took water level data from points, these black points, again, are monitoring wells, across. Here's our 3-mile radius around our modeled area. This is just an illustration of the water table map across the area. It's going from high, meaning red. Red is the higher water table, to low. So the groundwater flow direction is from the northwest to the southeast. With the water table measurements that are done out there, the natural resources districts in the area collect water level measurements once a year in the spring to show the high water table elevation. And that gives you one point in time each year, the highest water level in the area. We wanted to simulate the effects during the highest usage time period, of course, and see what the effects would be on the other wells in the area. So we took into account the United States Geological Survey data at a well in a town called Roseland, about 10 miles away, just to illustrate that the fact that the water table data that we get from the NRDs and used in our model shows us the water level data at the time each year in the spring at this point, the high point of the year. In the USGS monitoring well, they took a measurement every month. And you can see that during the month of July in 1992, there was a drawdown of about 30 feet during the irrigation season. So in simulating our groundwater model of the area, we needed to account for the fact that not only is the water table fluctuating over the years, but throughout the year, you see quite a significant decrease during irrigation. And the other thing to note was that from about 2001 on, there was a decline due to a drought in this area. So those are the kinds of things that we gained from looking at the USGS water level data in the area. It goes beyond what you can get from the annual water level measurements collected by the NRDs. Then what we do is we take the information that was gathered from the water level measurement points from the NRD, and we put that information into our groundwater model. And so that's what we call, in this diagram, the observed water level measurements. And as I said before, these are the water level measurements taken once a year in the spring over the 20-year period. And the blue lines, the blue dashed lines, are model's interpretation of the water levels over that period. And as you can see, this is the process of groundwater modeling incorporates a period of calibration where you're calibrating your model to make sure that it is consistent with the reality of the measurements taken. And this one I'm showing you here does have fairly good consistency with the high water level measurements corresponding with the high water table computed values in the model. But as you go back in time, you can see that the model was off for a period of time in the beginning simulations. And so those are the kinds of things that we work on in calibrating the model, try to make it match up throughout the entire period. But the important thing also is to note is that the model was simulating the significant drawdown during irrigation season, so that the impact of the new wells can be superimposed on the impacts of the natural conditions out there. So what we did was we took the groundwater model, ran it a couple different scenarios, and looked at what are the impacts to the wells. I'm just going to, you don't have to look at it in a whole lot of detail in this table, but basically for every registered well out there within that 3-mile area, we did calculate what the final drawdown would be after that 20-year period with that, with the new well pumping. And we did a calculation as well, looking at each of those wells. This, again, just a bunch of numbers that we put together to identify what the impact, what was the loss in yield for each of those irrigation, or it could be irrigation or industrial wells. The bottom line was that we saw the estimated impacts in the area to be anywhere from 2 to 17 feet, with both those wells running at the capacity required throughout the year to keep that power plant running. The good news was the 17-foot drawdown was just immediately around those 2 wells, and they were actually wells that were going to be utilized by the power plant themselves. They can use different water sources too. So those 2 wells that showed a 17-foot drawdown were not going to be an issue. The other ones, though, we did look at in detail, as I showed before in those tables. We did look to see if the wells that showed some significant impact, was there another well that this irrigator could use in their area, or what were the options that they had. Because some of them did have more than one well and could use the other wells for additional water source. But I want to bring back the point that the main idea here was not to use this as the primary water source. The plans are to use that 4,000 gallons a minute that the Army Naval Ammunition Depot is using, or is producing during the treatment of the contaminated water to the south. So these are just, this whole impact study hopefully will never be seen in reality. So in general, what we accomplished with these two studies is trying to answer the questions from our clients, the Natural Resources District, on how we can better manage our groundwater resources using the aquifer mapping and the GIS mapping. And for managers across Nebraska, understanding the extent of these aquifers is critical in managing their water systems. And I just bring this up to say that similar types of projects could be done in other parts of the country. It's just one method that we used and hopefully can be applied in different areas. The second question that we were asked by our clients was, will a new large water user impact wells in the area? And that, again, we used a groundwater modeling system. And I want to mention that the modeling is an expensive evaluation process, but for such large wells as we saw going in this area and the high demand seen in this part of Nebraska in terms of irrigation, the impact study is critical to ensure that you're not permitting beyond the means of the aquifer itself. So at that point, I'd just like to open it up to questions and also thank all the people that actually helped me in putting together these projects. These were not obviously done alone. We have a very fantastic GIS staff here at Olsson Associates, and they put together a lot of great maps and allowed us geologists to look at the data and use the information. As well, our clients, I'd like to thank the Lower Platte North Natural Resources District and as well the Hastings Utility and Nebraska Public Power Generation Authority.
All right, Karen, thanks. We do have a few questions. The first one is, why is the drawdown so symmetrical?
So that has to do with the aquifer itself. This is a fairly homogeneous aquifer. In areas where the aquifers are discontinuous, you would see a change in the shape of that drawdown. But when you do pump from a well, there's going to be what they call a cone of depression, and it is a circle. It's symmetrical. Unless there are geologic factors that are going to make it change and discontinuous in certain areas. There were some perturbations, I would say, it's not completely symmetrical, and that has to do with the fact that those other wells pumping in the area will affect the flow patterns as well. Good question, though.
I'm going to try and go back because I believe that...
I can go back, probably. Oh, you can, too.
On slide 15 here, we had a question, I think it was during this point, that asked, what is the vertical scale of the cross sections?
That's a great question. And it would have been really difficult to illustrate a whole lot of detail, any more detail on these. So I appreciate the question. I meant to mention that 200 feet is the maximum depth of the deepest ones on these.
Okay. A question I think was follow-up to the other question was, what level of drawdown would have been unacceptable?
You know, that's a really good question, and that we do leave up to the managers, the Natural Resources District Board of Directors. This aquifer that they were tapping into, the lower aquifer, is 100 feet thick. So if you saw 17 feet was the maximum, most of the wells were showing anywhere from 3 to 5 feet of drawdown. That's less than 10% difference. Those are the kinds of things that they decide based on what they know in the area. We just show them what the impacts are, and then the decisions are made by the Natural Resources Districts.
Okay. The second project that you talked about, the public power one, how long did that take was another question.
Marty Stang is our client. If he's out there listening, he'll recognize it took longer than we anticipated. It always does. That was a 6-month project, is what it ended up being.
Another question that just came in: did you use a pre- and post-processing software for modeling?
We did. We actually used 2 different ones. We used GMS, Groundwater Modeling Systems, GMS, I think that's the acronym, and the other one was Groundwater Vistas. They're both ModFlow-based systems. So.
Okay. Another question is climate change. Does the model have the capability to model long-term impact of climate change?
That's a really good question. What we tried to do in simulating those 20 years was look at the climate changes over a period of time where there was a drought period. And as they showed in one of the slides, you could see the water table hydrographs from the USGS well from 2001 to 2006 did show a decline during the drought period. We also had some highs in earlier parts of that modeled period. But yes, that's the intent, is to look at changes in climate based on historic record. As you look into the future, obviously the weather patterns and precipitation will change, and so you'll have to. These are the kinds of studies that should be done to simulate impacts due to global warming. If there were, if the models that are out there right now, what they're showing is that in the Midwest we'll see more frequent storms, high intensity storms. I'm sorry, lower frequency but higher intensity. And so those are the kinds of things that we should probably look at changing in our model patterns, precipitation patterns. That would be one way to do it.
Well, I think that's all the time for questions today. If you didn't get your question answered, up on the screen you see Kieran's email, and she'll be more than happy to respond to that, to your questions. So, first of all, we want to thank you for coming to our webinar today. That's co-sponsored by the Water Research Foundation. Shortly after we conclude today's webinar, you'll receive a survey evaluation for this webinar that you can email back to us. Please take a few minutes to complete it and give us your thoughts. And our next upcoming webinar is set for September 22nd around 2 p.m., where we will be showcasing our groundwater guardians and adult groundwater education. There's an archive version will be available of this webinar with Karen at our webinar button on groundwater.org website. As a registrant for this webinar, you'll receive